In this video, we will discuss binary particle swarm optimization algorithm, that is binary PSO. Traditional PSO we already discussed in previous videos using numerical examples, MATLAB code and Python code. Now we will try to understand what is binary particle swarm optimization algorithm. Here you can see different topics covered in this video. First we have particle swarm optimization algorithm key points. Next, what is binary PSO? We will try to understand this using numerical example. In the last one we have novel binary PSO. Due to certain limitations in binary PSO, the mathematical models are further modified, and the last one we have its modified version, that is novel binary PSO. Novel binary PSO is introduced in 2007. Different benchmark test functions are used to test its performance and it provides efficient results. So first we will discuss PSO key points. We will not discuss this algorithm in details as we already discussed it in previous videos. As we know, PSO, it is a population-based meta-heuristic optimization algorithm that we can use to solve different engineering optimization problems. So this algorithm is basically inspired by the Wurtz flocking behavior. Now suppose we have n agents and we will consider Wurtz as the particles. So suppose we have n particles and we have a search space. So first we will initialize the position for n agents in the search space. Now suppose we have n agents and they are randomly initialized in the multidimensional search space. Now each particle has their own position, and you can see they are randomly located at different locations in the search space. Now after population initialization phase, we will calculate fitness value for each agent, and then based on their fitness values, we will select personal best and global best. Personal best, that is their own fitness value. Global best is the fitness value that is best among all. So if we are solving minimization problem, so we will consider the minimum fitness value among all as the best value, and if we are doing maximization, then we will consider the maximum value as the best among all. So here we will compare agent's fitness value and then we will find out global best fitness value. After that, the main loop for this algorithm started here. For each particle in the current population, we will calculate their velocity. Initially their velocity is 0. So using this formula, we will calculate their new velocity. After that, we will calculate new position for each agent, as we here randomly initialized position in step 1. Now using this equation, we will update position for each agent in the search space. So here in the previous position, we will add the new velocity that we calculated and we will update their position. For example, here we have different particles in the search space and we can see their older position. Suppose we calculated velocity. Now we will update this particle position. So in this older position, we will add the new velocity and then we will update its position to another location. That's how we will do for all agents in the search space. After that, again using objective function, we will calculate fitness value for each agent. So here we will calculate the fitness value for their new position. As we updated here their position, so now we will calculate fitness value for the new positions and then again update local and the global best. We will repeat the loop until current iteration is less than or equal to maximum iterations. When the stopping condition is met, we will stop and display the best position and the best fitness value. Now suppose here this is the best agent among all. So we will consider this best solution and we will return its position and fitness value. Now we will try to understand binary PSO. The major difference between traditional PSO and binary PSO is search space representation, velocity interpretation, and variables management. For example, you can see here in traditional PSO, the solution space, that is the search space, is continuous. It means each particle in the current population can take real values as their position in each dimension. On the other hand, in binary PSO, search space is discrete and each particle is represented using binary vectors. So we have combination of 0, 1, 0, 1, 0, 1 that is used to represent each particle position in the binary PSO, and here we are using real values in traditional PSO. Next we have how velocity and the position is updated. As we already discussed, in traditional PSO, real valued arithmetic is used to update velocity and the position. In binary PSO, binary variables are used and it also involves sigmoid function to map real valued velocity and position into binary, that we will discuss in the upcoming slides. Both traditional PSO and binary PSO are applied to solve wide range of optimization problems and they provide efficient results. Here you can see the simple process is used in binary PSO. Now step by step we will try to understand this algorithm using numerical example. Here you can see the simple process. So first we will initialize the position for each agent in the search space randomly. After that, for each agent we will calculate the fitness values. After fitness value calculation, based on their fitness values, we will compare and select local and the global best. Next we will update the velocity for each agent in the current population, and then we will update their position, and then we will update their position, and after that for the new position again calculate fitness values, check the stopping condition. If it is met, then stop and display the best solution, else we will repeat this loop until stopping condition is met. First we have parameter initialization phase. Suppose we have 10 particles in the current population and dimension is 8, or you can say we have 8 design variables. Suppose maximum iteration we have 50, weight inertia 0.7, coefficient, and we have two coefficients C1, C2, 1.5 and 1.5. Now for 10 agents we will initialize their position in the search space. Xi, here I is 1 to n, it means value for I we have 1 to 10. So we have 10 particles. Position for the first particle is x11, x12 and so on. So next we will initialize the position for each particle. So here we have population of binary particles. So this is binary PSO, so we have population of binary particles. You can see the position for the first particle 01, 01, 01 and 01, for the second particle, third particle and up to last one. Now position is initialized for 10 particles. Now we will calculate the fitness value for each particle using objective function, and here we are using the sphere function, you can see here, to calculate fitness value for each agent in the current population. So first for the particle 1, you can see position we have 01, 01, 01, 01. Its fitness value, put all the values here in this function. So here we got the fitness value for first particle 4. For the second particle it is again 4. For third particle it is again 4. Suppose, and so on and so on. You can see for all the particles we calculated. It is 4. Fitness value for third particle is also 4 here. Like that for all the particles we will calculate the fitness value. After that we will save the local and the global best position for each particle. Suppose here local best is there. Local best, that is their personal best fitness value, is this one. Now suppose we are solving here maximization problem, and in the end we will display the particle having maximum number of ones. For simplicity we will use here just 5 particles. Now suppose the best particle we have third particle. Now we will calculate the velocity. for each particle based on their current velocity. So here you can see we will use this equation to calculate velocity, and after that we will apply here sigmoid function to map real value into binary velocity values. So here you can see, so here we need weight inertia W, random value we have 2, suppose this is R1, this is R2, 2 coefficient C1, C2. So here we have value for weight inertia 0.5, C1, C2 1.5, 1.5, and we have here 2 random values. You can see here, suppose it is R1, R2, R1 0.6, R2 0.4. Now here for the first particle position, you can see this one. Now we will calculate the velocity for first particle. Put the values in this equation. Weight inertia we have 0.5. Now this particle older velocity is 0, so we have vector 0 plus C1, that is 1.5 in the first random value. In the first random value R1 1.6, and plus we have C2 and second random number. So here we are doing the vector subtraction. So here you can see we have vectors. We will perform here vector subtraction. Suppose we have two vectors A and V. Inside A we have A1, A2, A3. Inside V we have V1, V2 and V3. Then if we want to multiply these two vectors, then first we have A into V, that is A1, V1, A2, V2, A3, V3. And if you want to perform addition, then it is A1 plus V1, A2 plus V2, A3 plus V3. So same you can see we have different vectors. So for each element we perform, and in the end you can see we obtain the velocity value for the first particle 0, 0, 0, minus 0.6, minus 0.6, 0, minus 0.6 and minus 0.6. Like that we will calculate for each particle. So suppose for simplicity we will consider only 5 particles. So for 5 particles we calculated the velocity values. Now you can see we have 0.6 minus 0.6, but we need all the values in the binary form. We have binary position, we need binary velocity. Now we will calculate the binary velocity. As we have the binary position, we need the binary velocity for each particle. So here we will apply the sigmoid function, you can see here, to each element to update the velocity vectors. So here this function is applied to map real value into binary velocity values. For first particle position you can see here this one. Now you can see for the first particle, now for each element we will calculate. First we have 0, then here e raised to power 0 is 1, 1 by 2, 0.5, next is again 0, next one is again 0, and here we have minus 0.6, and this is the approx value 0.354. Same we will do for rest bits. So we will round up the values and we obtain the binary velocity for the first particle 111,001,000. Same we will do for all particles. We obtain the binary velocity values for 5 particles now. After that we will update the position for each particle. So here you can see how we can update the position. So this mathematical equation is used to update the position for each particle. Now we'll update the binary position of each particle from left to right in the binary velocity vector, and we will use here this equation. So here you can see for the dimension 1 we have velocity value 1, for the dimension 2 it is 1, third 1, 0, 0 and 1, 0. Next you can see here Rij, that is a random value. So we need here 8 random values and we have 8 dimensions. So suppose we have 8 random values, you can see. Now put random value and compare. First random value 0.3 is less than velocity value we have 1, and as you can see if condition is true then it return 1. So we have 1. Next random value 0.6, condition is again true, so 1. Next condition is true, so 1. Next you can see it is 0.8 and here we have 0. Next condition is false, so we have 0. So like that for each dimension. Now you can see the updated binary position for the first particle. We have 1 1 1 0 0 1 0 0 for each particle. Now for each particle we will update their position and we obtain the binary position for the each particle. Now you can see this is the new updated position. Now using fitness function we will update the new solution. So here again we will apply this pair function and we obtain the new fitness value for 5 particles. We will repeat the loop until the stopping condition is met, and once the stopping condition is met we will display the best solution. Binary PSO has certain limitations, as you can see here in its parameters and in memory. So for more detail you can follow the research paper. Now we have noble binary particle swarm optimizer. Now step by step we will see how binary PSO is working, again using the medical example. First, initialize the position randomly in the search space as we done for PSO, and for binary PSO calculate the fitness values, compare agent's position, it means their fitness values here, and we will save their personal best and the global best fitness values. After that we will change particle velocity. In noble binary PSO, 2 velocity vectors are used for each particle. Now for first particle we will calculate, and different rules are followed here. When the p best is 1, then we will use the values for, then we will use these two values and put in these equations. When it is 0, then we will follow this. When the g best is 1 and 0. Now for the first particle we have position 0 1 0 1 0 1 0 1. For the 8 bits you can see we calculated here 2 velocity vectors. Just put the values here and calculate. Now we will calculate first particle velocity. For this we will use this new formula here. This is the velocity complement. Here if the bit is 1, then here if the position bit is 0, then we will consider the first vector value, else when the position bit is 1, then we will consider the second vector value. Now here you can see we calculated the values. Now here we will follow this model. So first bit, so for the first particle you can see position we have 0 1 0 1 0 1. First bit we have 0, so when it is 0 we will follow Vij1. Vij1 value we have 0.00. Now for the second bit it is 1. Now you can see when Xij is 1 we will choose this one Vij0. In Vij0 we have 0.09. Next for the third bit it is 0, so we will follow this one. So we have third bit 0.00. Next bit is 1, so we will follow 0 here for this one, that is 0.11. Like that we will do for all the bits, and we obtained here the complement for each bit. After that we will generate the random variable within 0 and 1. So here Rij, that is the random value we will use here. So this is normally distributed between 0 and 1. Here you can see this is the random value that we will compare with the velocity complement, and then we will update the new position for the each particle in the current population. So here we used 8 random values. You can see 8 random values here: 0.78, 0.25, 0.665 and so on. And here we will put the complement values, and here we will put the complement values that we calculated here. So here you can see we put all the values for the all complement. So after comparison you can see we obtain 0 1 0 1, again new combination. So this is the updated binary position for the first particle. Now you can see the new position is completely different than the older position. Older position 0 1 0 1 0 1 0 1. In the new position you can see here 0 1 0 0 1 1 0 0. Like that we will do. So like that we will do for all the particles, and we will update their position. After that we will calculate the new fitness value for each particle, then again save new personal best and the global best values, and we repeat the loop until the stopping condition is met. Personal best, global best, and here again we will change the velocity bit, generate new velocity, new, and generate new position. Repeat the loop until the stopping condition is met, and when the stopping condition is met, we will display the best solution that is found in the last iteration. Binary PSO has simple algorithmic structure due to its discrete nature, and it is commonly used in applications such as feature selection in machine learning. So that's all about this video. If you have any questions, you can comment below, and thanks for watching this video.